Okay, so in this lecture, I want to discuss organometallics, which broadly speaking is a wide range of organic molecules or compounds where you have at least one carbon metal bond that is the reactive functional group of interest. So generally speaking, when I write the symbol R, I'm referring to some sp3, sp2, or sp hybridized carbon. And the electronegativity of carbon is roughly 2.5 on the Pauling scale. And the metal that is bound, M, normally has an electronegativity value between 1 and 2, but they can vary. So this carbon metal bond is highly polarized, where that bond dipole points towards the more electronegative atom. And thus there's a great deal of partial negative and basic character. All right, the carbon is electron rich, while the less electronegative metal is electron poor. And so an organometallic, for your purposes, can be approximated as the following. Basically, a pseudo-ionic interaction where you take this carbon metal sigma electron density and you treat it as if it's a lone pair. And it's not truly a lone pair, but you can get away with this approximation in introductory organic chemistry, as if the metal is just a positive counterion next to the carbanion. So it is carbanion-like. Or in other words, this compound and its reactivity are correctly summarized by treating it as a pseudo-ionic species. In other words, this bond is weakly covalent. So we're going to see that it's highly reactive and it reacts as a carbanion. So before we start to delve into the different types of organometallic species, we should explore the various electronegativity values. So lithium's electronegativity value is just about 1. Magnesium is 1.2. Copper 1.9. And carbon's 2.5, as I said. So the important part is that carbon is the most electronegative by far in this series. And therefore, you can think of the extent of polarization of the carbon metal bond as the extent of how ionic that C metal bond is, or the more carbanion-like if you have a greater bond dipole. So the carbon lithium dipole is the greatest, and magnesium is a bit smaller. And the cuprate, both of these bonds are slightly less polarized than the others. So for the Grignard and the organolithium, they are highly basic. Really, the organolithium is a little bit more reactive than the Grignard. And a much less reactive species is this organocuprate because of the lower electronegativity difference between copper and carbon, where copper is the most electronegative metal in this series, while lithium is the least electronegative metal. So the most ionic-like, or the one that's the most carbanion-like, is the organolithium, followed by the Grignard, and that's followed by the organocuprate. So these two, the Grignard and the organolithium, sort of stand alone, and that they have very similar reactivities. And in this course, they are going to do reactions as bases and as nucleophiles in the same ways, pretty much indistinguishable of one another. But the cuprate is going to be less carbanion-like, less basic, and it's going to have a more selective reactivity. You can think of it as being weaker if you'd like. So the names for each of these functional groups are as follows. An organomagnesium halide is a Grignard. Organolithium, when you have a carbon lithium single bond. And then an organocuprate is when you have this dialkyl cuprate, where you have these two identical alkyl groups. In this case, they're ethyl groups. That's also known as a Gilman reagent. So the above organometallics are each basic. Any carbon with electron density is basic, and or at least with a great deal of dense electron density that's unstabilized, and nucleophilic as well. And we generally desire the nucleophilic character. Sometimes we use them as strong bases, but usually as organic chemists, we're interested in making new carbon-carbon bonds, and it's very convenient to have carbon nucleophiles to do that with. But the most basic one is listed above as number 1, the organolithium, and that's more basic than the Grignard, once again resulting from a greater carbanion character at the carbon in the organolithium. And then the organocuprate is the least basic of all. So the most ionic is the most basic. So before you can use these in synthesis, you must know how to prepare them from some other functional group. And normally the functional group you make them from is an alkyl, vinyl, or aryl halide. And you can do it from any of those three. The first one here is vinyl, where you have an sp2 carbon bound to bromine. The next is aryl, where you have the sp2 carbon of an aromatic ring, like benzene, bound to a halide. And then alkyl. And these work for all three organometallics. I'm just using random examples of various halides here. And the Grignard is best prepared from going with the bromide, solid magnesium in the zero oxidation state in an ether solvent, such as THF or diethyl ether. And magnesium inserts itself via a radical mechanism so that now each of the halide, or the halide and the carbon, each of the nonmetals is bound to magnesium and taking electron density away from it. So magnesium has basically been oxidized during this process from 0 to +2. And that indicates the carbon is now electron rich with a -1 formal oxidation state. Chlorobenzene can be turned into an organolithium with 2 equivalents of lithium in the zero oxidation state. And normally that's done in a hexane or could be an ether solvent. The side product here is lithium chloride. That's why you need 2 equivalents of lithium. And unlike magnesium, lithium simply goes from 0 to +1, or only loses 1 electron, and the carbon is now in the -1 oxidation state. If you want to go from an alkyl bromide to a cuprate, it's a 2-step process where you must first make the organolithium. And this is done by the same procedure as above, with 2 equivalents of lithium, 0, it's a solid, and hexane. And you get 2 equivalents here of the ethyl lithium if you start with 2 equivalents of ethyl bromide. And from there, you add 1 equivalent of copper iodide. And that will allow for transmetallation to occur, where the alkyl groups swap the metal that they are bound to for an electronegativity reason. And that gives you your organocuprate. Now, when you have this, you're just going to treat it like an ethyl group as an anion. That's basically how it behaves for your purposes. Okay, there are 2 of them, but they are always the same, and you never have to decide which one is more reactive. Okay, and only one of them ends up reacting. We would treat this organolithium as if it's a benzene with a negative charge. That's how it will behave. And then the Grignard we would treat as a vinyl group with a negative charge. So once you have that metal, you can treat it as an ionic compound where it's a great nucleophile and a strong base. Now what you notice here is that we have pretty much nonpolar and certainly aprotic solvents that are being used. And the reason for that is because protic solvents, which are OH, NH containing, or hydrogen bonding, occurs in a protic solution. These solvents are acidic. And that acidity is going to ruin your organometallic that you went into the trouble of making. Because as soon as the organometallic is made, it is a very, very basic carbanion, like this ethyl ion here. And the acidic solvent that is in excess surrounding that ion will quench or do an exothermic acid-base reaction with the strong base, the organometallic. And we will do some examples of those quenching processes in just a second. So, as I mentioned, organometallics, first and foremost, are really more than strong. They are super bases. And they desire H+. Anything that can give a proton to this strong base is going to do so irreversibly. Okay. Or they will deprotonate anything with a pKa below 40 or so, including that protic solvent, if it's around. Next, they are good nucleophiles, but this process is slower than a simple acid-base proton transfer. But we're usually interested in using them as good nucleophiles, so we think about how we avoid them from acting as super bases in the interest of getting to this second characteristic of nucleophilicity. So I'm going to rank the following Grignards from most to least basic, and this is just to show you that not all organometallics are made alike, even when you have the same metal involved, and it is highly dependent upon hybridization as to which is the most to least basic and most to least reactive, therefore. So to do this, you should basically go ahead and draw the ionic type representation where we cleave this carbon-magnesium sigma bond and treat it as a carbanion lone pair. So notice here that I've broken this bond between carbon and magnesium in each case. It is no longer a bond, it is this lone pair on the carbon. So the difference among these carbons in the series is hybridization, right? The alkyne is sp hybridized, the alkane is sp3 hybridized, and the alkene is sp2 hybridized. And remember that sp hybridized means 50% S character, 50% P character, whereas sp3 is 1 part S and 3 parts P, so it's 25% S character. sp2 is 1 part S and 2 parts P, or it's 1/3 S character. And the most S character is the carbon that is most electronegative, which means that the sp3 carbon is the least electronegative. And therefore, the most basic is going to be the carbanion that is least stable, or the negative charge on the least electronegative atom. So sp3 or alkyl Grignards are more basic and more reactive than vinyl Grignards. More S character makes that lone pair more stable. And sp are the most stable and least basic of all. Okay. So there's some solvents below, and I just want to give you some examples of which solvents would be useful for synthesizing and or using an organometallic like a Grignard. And in this case, making the Grignard is what we're going to do from that vinyl bromide compound that we used in the past. So the names of these solvents are diethyl ether, ET2O, you'll see it written like that, ethanol, ETOH, acetone, tetrahydrofuran, acetic acid, and dichloromethane, DCM, or methylene chloride. So what you cannot have is any electrophiles or any acidic protons. So the two protic solvents with OH bonds that are hydrogen bonding, acetic acid and ethanol, these are out because these would quench the organometallic as soon as it is made. This proton here would be deprotonated by a strong base. And we'll do that reaction in a minute. You do not want to use DCM because you have chlorides here. And so you could get what's called transmetallation, or you could get exchange where the DCM turns into an organometallic. So we do not want halogenated solvents because the way that a Grignard forms is from halogenation, or insertion into a carbon-halogen bond, I should say. Ether solvents are good because these only have sp3 CH bonds, which are not acidic. There's no hydrogens on electronegative atoms, and it's only slightly polar. Okay, so ethers are barely polar. THF a little more so than diethyl ether. So this is an appropriate solvent with no halogens and no acidic protons, and therefore the ether is also an appropriate solvent. But acetone is electrophilic. As you may know from carbonyl chemistry, that carbonyl carbon will react with nucleophiles, or there's a great deal of delta positive character here. And the protons that are alpha to the carbonyl are also acidic, as you may know from enolate chemistry. So those alpha protons would quench the organometallic once it's formed. So the only two suitable solvents here are diethyl ether and THF, which we will see a lot in example problems. And below, I simply want to explain in reaction terms why each of those solvents was or was not an appropriate choice. So with acetic acid and ethanol, they are both pretty acidic relative to a hydrocarbon, where acetic acid has a pKa of 5 and ethanol has a pKa of 17. And the Grignard would simply break the carbon-magnesium bond, transfer a proton to that alkene carbon, and give you acetate as the conjugate base. So this gives you ethene or ethylene. Magnesium bromide now sits here next to the oxygen. And there's a new hydrogen on the end of the alkane. But I'm not going to draw that because there are three other hydrogens that were already there. And it's implicit. There's now a fourth hydrogen in this molecule. And ethylene has a pKa of, 45 or so. But the equilibrium constant, of course, for proton transfer is 10 to the difference in pKa's, product minus reactant. or 10 to the 40. And ethylene is also a gas, which is going to allow it to evolve from the solution and drive the reaction to completion. So this reaction would do quenching. And therefore, acetic acid is a poor choice of a solvent because your Grignard is consumed irreversibly. It's a large equilibrium constant, this process occurs. And you can't use it as a nucleophile. A similar process happens for ethanol, where we deprotonate to make the ethoxide ion, and you get ethene. Now the equilibrium constant's a bit smaller, but it's still infinitely large, and therefore this process is irreversible. For acetone, you could imagine that because of the CO bond and its polarity, that the electrophilic character at carbon is going to allow the Grignard to attack directly there, which would break the pi bond. So it undergoes nucleophilic addition. And then magnesium, once again, will sit next to O minus. So in all of these cases, we go from the carbon having the negative charge, because it was bound to a metal, to an ionic-like interaction between highly electronegative oxygen and magnesium in each of these. Or we let the negative charge sit on the more electronegative oxygen, as opposed to in a Grignard where it was localized on carbon. I mentioned that ketones have alpha protons that are also acidic. And so the Grignard, perhaps, if it doesn't chelate to the carbonyl, it could deprotonate and form what's known as an enolate conjugate base. And the pKa here is roughly 20 for alpha protons adjacent to ketones. And that's still way more acidic than ethylene. So that gas evolves from the solution, and the large pKa difference would cause this quenching process to have an equilibrium constant that is infinitely large, 10 to the 25, and irreversible. With a chloride, what you might get is an acid-base reaction as well, because of the acidity of DCM. There's two electronegative atoms that are withdrawing. The reality in this case is now that we have a carbanion that is poised to lose a leaving group so that it can satisfy that negative charge, where that anion is more stable on the chloride leaving group. This gives you a reactive carbene, which might go on to react with alkenes via cyclopropanation. Now that may not be a reaction you've learned, but just know that this is going to be a poor choice of solvent because of side reactions. Okay, so if we choose the correct solvent and we can get the reaction to go without some side reaction like acid-base, etc., that's undesired, then we need to know which functional groups, which electrophiles are appropriate to use or sufficiently reactive to react with each of these organometallic types. So organolithiums are the most basic of all, and we said that they're going to be highly reactive, and they will react with epoxides, aldehydes, and ketones. However, their reactions with alkyl bromides do not give clean product mixtures, and they give a mix of what's called transmetallation products. So we generally don't do those reactions. And in this class, Grignards and organolithiums react almost identically, okay, with lithiums being the more basic of the two, where their reactions with aryl or alkyl bromides are not clean, but epoxides, aldehydes, and ketones are all lightning fast. Organocuprates, we said, were less carbanion-like, sort of the weaker version, and therefore more selective. But the bond angle strain of an epoxide, this three-membered ring, and its desire to break open when it behaves as an electrophile will allow cuprates to do that reaction as well. And aldehydes are sufficiently electrophilic. They lack steric hindrance because they simply have a hydrogen with carbonyl. However, ketones are bulkier, less electrophilic, and react very slow with cuprates. But the one thing that the cuprates do that the others do not is they will react with aryl or alkyl bromides via a substitution-like reaction, or it gives you a substitution result.